there are many cases where we have a large number of explanatory variables, and our aim is to produce a model which makes sense, but also it's parsimonious, it's simpler. So we have this variable selection problem that can be also very complicated. So today's talk will mostly be on Bayesian ideas. I think it has 3 different levels, so I'm going to spend more time on the first part, try to show you why I think you should do variable selection using the Bayesian approach. So we're going to have a big discussion on that. Then the talk will go to the second level, and it's going to be a little bit more difficult. I'm going to show you some details on different type of models, and by different type of models we're going to mean different type of priors under the Bayesian perspective. So it's going to be a little bit more technical, and at the end, if we have some time, I want to just briefly mention to you what I'm doing lately. So I'm going to give you a very quick flavor of my last research work. So since this is an introduction, I have produced a PDF file for you that it's on my website, and I can come back to this slide at the end, so you can write a link and you can use it. There is a lot of material there. You can find some references. So, you know, the idea is to download this and then read some papers and start working with these Bayesian ideas. So this is a synopsis of a talk. Let's skip it and let's start with an introduction. And I like this introduction because it shows exactly what I think is the main problem here. So let's start with the general question: what is model selection? Okay? Well, I think model selection is the evaluation of performance of scientific scenarios. And then we always come to this question: selection of the best. And what do we really mean by selection of the best? It's really the best model. And as a Bayesian, I think that the best performed model is totally subjective. And I can give you an example about that. When I was, many years ago, when I was a PhD student, I was working with this very nice data set that had to do with evaluation of hospitals. Okay? So we ended up using a model, and we wanted to compare actual with observed with expected outcomes that were related to patients, based on many covariates, many explanatory variables that were sickness indicators. So we ended up eventually having to solve a very difficult variable selection problem. And the special point about this variable selection problem was that there was some data collection cost. So in order to get information of the explanatory variables, you had to spend money. So some sickness indicators, they were very expensive, some other sickness indicators, they were not so expensive. So, you know, we wanted to create a model which was, on the one hand, clinically reasonable, but on the other hand, cost-effective, not so expensive. So we finally create a utility function, a structure, a function that we try in this function to include both these components, and we managed to solve the problem, coming with a model that was not so expensive but also had good prediction as well. And I think that in general, it might not be possible to find a single model capturing the preference of all relevant stakeholders in any visited model. So, for example, in the application I just mentioned to you, if you see it from the government perspective, you know, cost is very important. So he would like to see a model which is okay in terms of prediction, but really cheap if possible. If you see it from the side of the patient, he of course doesn't care about the money. He cares about how well he will be treated from the hospital. So, you know, it depends on how you look at the problem. You can think of different best type of models. And of course, different procedures of scientists support different completely models, and we have this very famous and well-known quote by this great statistician, George Box, that all models are wrong, but some are useful. And I totally agree about that. And I think that there is not always a necessity to go and select just one single model. Probably you can select a number of models and then try to find an approach that draws information from all these models on a nice way. And you know, when we do model selection, there is always a big battle. And this battle is between goodness of fit on the one hand and parsimony principle on the other hand. So, you know, in science, and I like this, we want to be simple. So, well, why not to use a simple model when we can, instead of a very complicated model? So, you know, it's always this battle, okay? Parsimony versus goodness of fit. And of course, model selection can be seen as a hypothesis testing problem. So, in a very simple scenario, when you want to compare just two models, M0 and M1, you can think of a hypothesis testing problem. So, this is the null, this is the alternative model, or hypothesis. And then, you know, if you like to do frequentist stuff, then, well, you have to assume the usual way, you know, you treat hypothesis testing problems, you have to assume that the null hypothesis is true. You calculate the test statistics based on the data that you have, you find these nice p-values, and you know, you compare this with a level of significance and you draw a decision. And of course, this approach has several limitations. The models have to be nested, there are cases where the likelihood principle is violated, and of course we have this usual problem of interpretation of the p-values, and of course the p-values, they don't have this interpretation that usually we would like to have as a weight of evidence in favor of, let's say, M0. Okay, so we are not allowed to say accept M0, but only fail to reject, as we all know. As we're going to see in a while, under the Bayesian approach, we don't have these issues anymore, because we're going to be able to place probabilities under each hypothesis. In other ways, we're going to make possible this interpretation here, so we're going to calculate actual weights, that we're going to call them posterior weights, of the two hypotheses or the two models, and therefore we can quantify our uncertainty about model selection. These are some available methods when you do, for example, either classical or Bayesian model selection, and we're going to discuss some of these in a while. If I mostly now focus on variable selection, which is of course a special case of model selection, then, well, still there are many scientists that they like to use these stepwise procedures. Don't do it, really. It's the worst thing you can do nowadays, really. It's completely suboptimal, and you have all these issues by doing these stepwise procedures. You know, you end up with p-values that for large data set, even if they have a small values, the hypothesized model is plausible. There are sequential applications of single significant tests, and therefore the exact significant level cannot be calculated. You ignore model uncertainty, you can compare only nested models, different procedures end up to different selected models. So, you know, there are all these, you know, issues when you do these stepwise model procedures, okay, for variable selection. Let's see how the Bayesian community would deal with this problem. So I think this slide is very important because it really introduces the problem, how a Bayesian would look to a model selection issue. So, I hope that you are a bit familiar with the Bayesian approach. So, under the Bayesian approach, first of all, the Bayesian approach is fundamentally probabilistic, okay? So, we have a joint probability distribution to describe the relationship between all the unknowns and the data. Under the Bayesian approach, the unknowns, in other words, the parameters, are treated as random variables. And therefore, we start by introducing prior distributions before getting the data, that represents our prior knowledge about all these unknowns. And this joint distribution then is obtained by introducing this prior distribution on all the unknowns. And then what we do, we update our knowledge by introducing data and by calculating a conditional probability of these unknowns based on the data that we have. And we call this posterior distribution, and all our inference is based on this posterior distribution. So this is what we do in simple inferential problems. Now, in model selection problems, we can do exactly the same. But now we also can have a large number of different models that are other considerations for the data. And so we have models, and other models we have parameters. So we can say that our space now, it has been augmented. So we have something like a transdimensional space where our space of all the unknowns, it's models and parameters, models and parameters. Okay, so all these are the unknowns now, and we try again to place a prior on all these unknowns to the models and the parameters, and then the joint distribution can be obtained, and then conditioning on the data, we can conclude posterior distributions. that can serve as model uncertainty and can be used for model selection, inference, and decision making. Okay? So variable selection, of course, as I said, is a special case of model selection, where each model corresponds to a distinct subset of the available explanatory variables. And in order to apply this technique, you have two main challenges: specification of the prior distributions and calculation of the posterior, as always, under the Bayesian perspective. Okay, so let's now focus to variable selection. So within the Bayesian framework, let's suppose that we have P explanatory variables, okay, and we want to do a variable selection problem, so we want to choose, for example, a single model or some good models. That means that we have a space, calligraphic M, of 2 to the power of P competitors, okay, and then what we can do, since we are Bayesians, we can calculate posterior model probabilities. In other words, we can calculate the posterior probability of model Mk given data Y, and if we use Bayes' formula here, then we have this ratio. So let's go to see how this ratio looks. In the numerator, we have this guy here. This is what we call marginal likelihood, or prior predictive, or model evidence. And this is a function of the data given model Mk. Here we have a function only of the model Mk. This is the prior distribution that we're going to place in model Mk. And of course, down here we have a sum of all these guys, of this evaluation here. So this is the normalizing constant. Okay? Now, what about this marginal likelihood? Well, this marginal likelihood now can be further expanded to include the effect of the parameters. So it can be written, if we assume that model Mk has parameters theta k, can be written as this integral here. So now here we have the likelihood. So this is the usual likelihood in statistics, f of y given the parameters of model k, given that we are in model k. And here we have another conditional distribution. This is the distribution of the parameters theta k given that we are on model Mk. And this is the second type of prior that we have to introduce in our approach. So you see already that when we perform this approach, we're doing exactly what I told you on the previous slide. We have two different types of priors. We have the prior on the model space, and we have the prior on the parameter space. Okay? Okay, now this looks nice, this looks easy. Well, as a matter of fact, it's not so easy. Let's see what can go wrong. Well, first of all, this integral here can go wrong. This integral can be multidimensional, can be very, very difficult to evaluate it, so you need to find techniques to estimate it. And secondly, this space here can be enormous if P is large. This space can be huge, so you might not even be able to calculate guys like that because you cannot calculate the normalizing constant, you cannot do the summation. Okay, so you need to find clever optimization algorithms to search this huge space. I'll come back to that in a while. Meanwhile, let's suppose that you can calculate things are not difficult, then of course you can start making comparisons. Very simple comparisons. So for example, if I would like to compare model Mk with model ML, I can just compare their posterior distributions, their posterior probabilities. So I just can create things like the ratio that I call posterior odds. So this is the ratio of the two posterior model probabilities. And if you apply here again Bayes' formula, the normalizing constant will cancel out. So this ratio here will end up being the ratio of the marginal likelihood. And this is what we call Bayes factor, times the prior odds, the ratio of the two prior probabilities. So you see that this guy here, Bayes factor, plays a really important role when we apply this technique. And as a matter of fact, it's a very simple exercise to rewrite everything in terms of the Bayes factor, so you can write entirely all these posterior model probabilities as a function of the Bayes factor and the prior odds. Okay? And then we have this beautiful paper back in 1995 by Cass and Rafterman in JASA that they gave a very nice interpretation of the Bayes factor. So they created a table like this, where for different values of the Bayes factor or the log Bayes factor, they came to conclusions that they were, in a sense, similar to conclusions that we come with p-values, so evidence against the null hypothesis. And this is the summary based on these different values of the p-values, of the Bayes factors. And I love this idea. I think this is the beauty of Bayesian statistics when you do model selection. This is a beautiful idea that we call it Bayesian model averaging. So when working with Bayes factors, the decision space, of course, involves the choice of a model that is then used for inference of prediction. But if the chosen model is only one of many possibilities, we run the risk that model uncertainty would be ignored. And this is something that we don't want, really. So, for example, imagine the situation where you end up calculating these posterior model probabilities, and the best model is a model with a posterior model probability of 28%, and then there is another model with posterior model probability 27%. Do we really believe that the first model is much better than the second model? Well, why not include both models when we like, for example, to do predictions? And this is exactly what we can do with BMA, with Bayesian model averaging. In other words, it makes much more sense to look at the panoply of some good, let's say K in total models, and then inferences of predictions they would give. So, for example, suppose that we are interested in a quantity, which let's call it capital delta. For example, this capital delta can be a future observation. Then, instead of reporting the predictive distribution of this future observation based on only the best model, well, we can take a weighted average of the posterior probabilities of delta under each model and use weights that are given by the posterior probabilities of the models in questions. In other words, so I'm not going to obtain my prediction only on the best model. I'm going to take the prediction of the best model, of the second best model, on the third best model, and all these predictions, I'm going to weight them with weights that there are given by the posterior model probability. So, of course, I'm going to give more emphasis on the very, very best model because it has the highest posterior model probability. So I can use information across many, many different models, good models, in a sense. So this is a very nice technique. For more on this technique, please read this very nicely written paper by Raftery in JASA. And these are back the issues that I told you before when we try to apply this technique. So, for example, it might be a problem to evaluate marginal likelihoods, and there are several ways that you can approximate it. Laplace approximation, for example, or you can try Monte Carlo estimates, although in practice they don't work so much and so good. And then there is this cheap estimator, MCMC estimates that people are using. And of course there is the work of Niall Fry, our friend here, that he has done a lot of work on estimating this marginal likelihood by written some really nice papers. The second problem here is the exploration of the model space. So what if the model space is huge? Then you need to run, for example, an optimization algorithm. So you need a clever optimization algorithm that will go through this huge space, avoid local optimum, and still be able, to capture the optimum in this space. Okay? And there is a lot of work also that has been done in this area. I have done a lot of work in this area as well, with David Raper, but also alone in a paper in the European Journal of Operational Research. So, there are a bunch of stochastical optimization algorithms that you can use, and they work really good, especially in these variable selection problems. And also you can do things like MCMC here, and I'm not sure how familiar you are with MCMC ideas. So, the whole idea is to create a Markov chain that has a specific stationary distribution, the distribution of interest, and then you have to wait until stationarity, and then, you get a sample from this stationary distribution. And you can do the same here in this transdimensional space. So eventually, your MCMC algorithm will come out to give you a sample from the best model. Okay? So this is how this algorithm works. And I think the most popular one is this reversible jump MCMC algorithm by Peter Green in 1995. This slide gives you an alternative representation when you do variable selection. So, and this is nice because it can simplify a bit the problem. So, you can represent all the competing models by a binary indicator vector, gamma, with zeros and ones. With values 0s and 1s. So, for example, gamma j here will take the value 1 if variable j is included in the model and 0 otherwise. Okay? So, for example, the null model without explanatory variables is the model that has all zeros. And the full model with all explanatory variables, it will be the model with all ones. Okay? Okay, so let's go now to the second part of the talk, priors. So, this is a very important area. So when you want to do variable selection, in a way you have to see which model you're going to use. And a model under the Bayesian perspective, it's the likelihood but also the prior. Usually we know the likelihood, so we start with a known format, so for example a normal linear regression. And then when we say we're going to use a different technique under the Bayesian approach, we really mean we're going to use a different priors. Okay? And then we have to check how good this technique is by doing several tests or by checking things like consistency or if we avoid some paradoxes, etc., etc. So I'm going to show you some ideas briefly. And as I said, we have two different types of priors, and I'm going to mostly focus on the prior on the parameter space, but I'm going to start with a very quick discussion on the prior on the model space. So the usual choice for the prior in the model space is to use a discrete uniform distribution, in other words, to give exactly the same weight in each competing model. If you think of a problem in terms of the binary indicators I told you before, this is exactly equivalent by putting a prior on the gamma j's like a Bernoulli 05. But you know, this prior might look quite normal to you, and we just put the same weight in each model, but there are many researchers that they argue that this prior, as a matter of fact, is quite informative and not non-informative, if this is your aim, because it puts more weight on models of size close to p over 2. Okay? And of course you can generalize this idea by changing this number here and use different numbers, so different Bernoullis if you wish. And this is what usually nowadays most of the researchers are using, so this is an idea by Lee and Steele with a beta binomial hierarchical prior. So they started by denoting by d gamma the model size, so you start with the model size, and they placed a binomial prior on the model size of the model gamma, binomial p comma theta, p is the number of the explanatory variables, and then this prior had a hierarchical form, so in theta they placed a different prior which was beta with hyperparameters alpha comma beta. Okay? And then the usual choice for these two hyperparameters is to take them equal to 1, and if you do so, you end up with a prior which is now uniform on the model size, not on the model space like before. Okay? Okay, and now let's move on to the prior and the model parameters, and I'm going to stay to that in a while. So let's start with a very, very simple model. Let's suppose that we have to solve a variable selection problem for a normal linear regression. Okay, so this is my likelihood. So these are my models. I'm uncertain about the x's, so x are the explanatory variables. So my parameter space are the betas and the sigma square. So I have to place a prior on the betas and the sigma square. Well, I can find in this case a conjugate prior, and my conjugate prior would have this format here. So it's going to be a normal prior on the betas given sigma squared and an inverse gamma prior on the sigma square. Okay? This normal prior will have a mean that we call it mu and a covariance matrix which is g squared times vm times sigma squared. And of course the main issue here is the specification of this covariance matrix. And you know, we have to be very careful here, and I'm going to show you in a while why we have to be very careful. So, you know, again, usually when we want to be to use non-informative priors or priors that they don't have a lot of information in Bayesian statistics, usually what we do is we take our prior and we make it eventually flat, okay, by having a huge variance, a very large variance. I'm going to show you in a while that this is not a very good idea to do here, because you may end up with really strange results with a paradox, which is well known. So you have to be very, very careful on how you specify this covariance matrix here, because if you use large, very large values, you end up with a paradox. So this is a problem. And with this type of priors, conjugate priors that have, on the other hand, the advantage that make all the calculations tractable because they are conjugate, Zellner worked a lot back in the 80s, and he just replaced this V of m with this x transpose x to the power of -1, and he created a prior that he called it a Zellner G prior. So the only problem about this prior now is the specification of this G. And again, this G plays a very important role. If you use a very large value of G, you end up having a prior which is almost diffuse, with a large, almost flat. If you use a very small value of G, you end with a very informative prior. So you have to really think a lot what type of values G should take. And the very, very common choice for G is to set G to be equal to N, especially for large data sets. Why is that? Well, if you place G to be equal to N, then you end up with a prior that has a name. We call this prior unit information prior. And why we call this prior unit information prior? Well, you can prove that the contribution of this prior to the final posterior is equal to only one data point. So if you have a huge data set, really this prior is low informative because it contributes to the actual posterior for only one data point. Okay? So by definition, for large N, this prior is low informative. This prior also can be easily extended to GLMs. And then there is this idea, and I like this idea very much, of Ibrahim and Chen, the power prior approach. And again, you probably remember that one of the big advantages of the Bayesian methodology is that it can work sequentially. Okay? So imagine that you have some historical data, and on this historical data you have calculated posterior distribution. Then of course you can take this posterior distribution today that you have collected some more data to use it as your prior in order to update your beliefs and calculate a new posterior distribution. And you can do exactly the same here. But what if I don't have historical data? Well, I know it's going to sound a bit strange, but you can imagine that you have historical data. You can generate some data. Okay? Well, I can generate some data, so I'm going to generate some imaginary data, fixed imaginary data, and this word is very important, fixed imaginary data, of size n star, and then my prior can simply be the posterior based on this data. Okay, but what if I don't believe on this data so much? Well, if you don't believe on this data so much, then raise the likelihood that really captures the information that this data have to a power. And if, for example, this power, 1 over delta, is equal to 1 over n star, then you really lower the information that these data have to the calculation of the final posterior. As a matter of fact, if you choose delta to be equal to n star, you end up with a unit information prior. It's like using only one imaginary data, in a sense. Okay? So this is the power prior approach with fixed imaginary data. And this is something that I have done, and I think it's a simple exercise. You can really easily show that there is, as a matter of fact, a connection between these very well-known G priors and power priors. So for example, this is the power prior in the normal linear regression setup, and you can see that it has the G prior structure with G equal delta, with these imaginary design matrices to be the initial design matrix, and with mean equal to this. So there is a strong connection between power priors and G priors. As a matter of fact, G priors are special power priors, okay, with specific fixed imaginary data. And these are some other ideas. So people, they also like, instead of a normal distribution, to work with distributions with fatter tails, like Cauchy. And this is a beautiful idea by Liang et al. Back in 2008, where they said, okay, we are Bayesians, okay, so we want to use the Zeller G prior, but we don't know what to set for G, what to use for G. Well, let's put a hyper prior on G. And this is exactly what they did. They used this beta for G over 1 plus G, this shrinkage parameter. And they call this approach hyper G approach. So they placed a prior on the variance of one of the components of the variance of the normal distribution, of the normal prior of the betas. Okay? And this is what they call a hyper G. And some years later, Beauvais and Held generalized this hyper G for GLMs. And also, you know, we can connect the priors with different shrinkages. So for example, if you use double exponential priors on the coefficients, then you end up with a lasso regression type. So you can have shrinkage type of priors. You can have many, many different things. And unfortunately, there is not enough time to go through all this information. Okay? This is the paradox I mentioned to you before, so you have to be very, very careful on the selection of the prior. So the paradox has a name. It's the Lindley-Bartlett paradox. So again, imagine that you have a variable selection problem. So you are completely uncertain about which covariates, which explanatory variables to include in your model. Okay? Then of course you can argue that since you are completely ignorant about which explanatory variables to include in the model, you would be completely ignorant about the coefficients of these explanatory variables. So it makes perfect sense to use a non-informative prior in the betas, correct? Well, how can you present this ignorance, this prior ignorance? Shall you use a diffuse prior in the betas, a normal distribution with a huge variance, for example? The answer is no, because when comparing two nested models with diffuse priors like this, then Bayes factor systematically favors the smaller model, regardless of the information in the data. So you will end up finally supporting the model with no covariates, even if the data says something completely else. In estimation theory, these non-normalizing constant cancel out, but this is not the case when you calculate Bayes factors. Because when you calculate Bayes factors, you calculate different models with different dimensions of parameters, and therefore these normalizing constants, they are not the same, so they do not cancel out. So when you use improper priors, the Bayes factors cannot be determined. So there is a lot of research back in the 90s on this issue, how you can use improper priors on model selection and still be able to calculate Bayes factors or variants of Bayes factors. So it was Aitken, first of all, that he applied this idea of the posterior Bayes factor, but he was clearly using the data twice, so they stopped using it. And then, approximately at the same period, Tonio Hagan and Jim Berger and Luis Perizzi, they start working with two different ideas. Tonio Hagan with the idea of the fractional Bayes factor, and Berger and Perizzi with the idea of the intrinsic Bayes factor. And I think intrinsic Bayes factor, it's truly a Bayesian approach, does not use data twice, so that's why people usually likes it a bit more. So I'm going to focus a little bit on this. And you know, the idea is very simple. It's like doing cross-validation in a sense, really. So this is intrinsic Bayes factor. So you use part of the data as a training sample, and then you use the resulting posterior as the prior for the remaining data. Yes? And because you're doing this approach twice, even if you start with an improper prior, the normalizing constants that will appeal twice, so they're going to cancel out. So you don't have problems. So you can calculate Bayes factors, intrinsic Bayes factors, this is how they call them, even with improper priors. Of course, we have the usual problem that we have in cross-validation, the dependence of the specific training sample. So if we don't want to have this dependence and we want to reduce it, we have to take many training samples and repeat this idea many times, if possible, all possible times. And then we can each time calculate a different intrinsic Bayes factor, and at the end take the average and calculate what Berger and Perizzi call arithmetic intrinsic Bayes factor. Okay? But what is really beautiful in this paper is that these two guys, after introducing this idea of the intrinsic Bayes factor, they moved a step further and they said, okay, now we have intrinsic Bayes factor, okay? Now let's think, can we find priors that would yield Bayes factors that are approximately equivalent to intrinsic Bayes factor in an asymptotic case? And they managed to find that priors, and they call these priors intrinsic priors. And I'm telling you from now, they look very nasty. They don't have a nice expression. They are very difficult to calculate, to be calculated. So it was almost 7 years later that Jim Berger was working with a PhD student named Perez, and they produced this beautiful idea in 2002 of the expected posterior prior that, as we're going to see in a while, is closely related to the intrinsic priors. So the idea is like that. So you remember probably how power priors work. I told you something like 10-15 minutes ago. So power priors, they used fixed imaginary data. Now expected posterior priors, they use again imaginary data, but this time random imaginary data, that they come from a specific predictive distribution. And then the only thing that you have to do is to average those data and calculate the posterior distribution of the parameter vector of the model under consideration. So the formula is really simple. So this is the expected posterior prior under model L, let's call it, for the parameters theta L. So you generate imaginary data, y star, from this predictive measure, let's call it m star, and then you just find the posterior distribution and take this average. Okay? And the reason why here I have used a superscript n is to emphasize you that in order to calculate this posterior distribution, of course you need to start with a prior. I'm going to call this prior Pn theta L, and this is going to be a type of baseline prior, which as a matter of fact it can be whatever, even improper, and you have no problems. Okay? So this has first of all a very nice interpretation. It's very simple. Now let's see implementation issues. So what about this guy here, m star? So this predictive distribution. What shall I choose for this predictive distribution? Well, Perez and Berger said that an attractive option leading to the so-called Bayes model approach arises from selecting a reference or Bayes model for the training sample and define this predictive distribution from where we generate this imaginary data as the marginal likelihood under the baseline prior of this null model. So use the marginal likelihood of this baseline model. For example, when you do variable selection, of course, you can think of the simplest model, and which one is going to be the simplest model when you do variable selection? The null model, with no explanatory variables. So, generate imaginary data from the marginal likelihood of the null model under a specific baseline prior. And this specific baseline prior can be whatever. It can be even improper, and you can prove that you have no issues. You can now calculate base factors without having problems because there are no normalizing constant. It's easy to solve that it cancels out. Okay? So there is no problem with impropriety if baseline priors there are improper. Also this m star can be improper, and again there is no problem because this m star is common to all the EPTs, so it's going to have the same normalizing constant. One of the nicest, I think, features of expected posterior priors is something that we call prior compatibility. When you create priors under the expected posterior prior approach, automatically your priors, they have the same base, this m star, so automatically they are compatible. And this is very important, okay? Especially if we have different dimensions. Okay, or if models are nested. So this is a very nice property of expected posterior priors. But they have some drawbacks, and this drawback I think mostly is on the variable selection problem. Excuse me. No problem. So under the variable selection problem, if you think about it, you don't only have to generate y stars, imaginary y data, but you also have to have some x stars, some imaginary design matrices. Okay? So let's suppose that y star is this. So this is the size, okay, and star. So how can we choose this guy here? Okay? So for example, you have your design matrix, so you have observed some data, and let's suppose that this design matrix here is an n by p matrix. Then what people would do in order to create imaginary design matrices, usually this n star would be smaller than n. So just simply go to your original design matrix with n rows and just randomly subtract n star rows. So create a submatrix, okay? N star times 3. But again, then you have this problem that we had in intrinsic base factor. So your final prior will not depend on the y star because the y star is integrated out according to the formula, but will strongly depend on this x star. And different x star matrices probably will result to completely different expected posterior priors. So how you select this x star? And this is the main issue here. Okay, so And I think the main issue here has two components. First of all, we have to see what n star will be. Shall it be a small number or shall it be a big number? Berger and Parisi, in general, they like this idea of the minimal training sample, where they say, well, since we use this y star data to build our prior, we don't have to use a lot, really. Use the smallest possible sample size. So put n star to be the smallest possible number in order, of course, to be able to calculate your posterior. So if you have p parameters, n star, of course, should be at least p in order to be able to calculate your posterior. So this is the minimal training sample. And so this is something that people can do. But then, if this n star, the minimal training sample size, it's much smaller than n, then of course this number of combinations, n over n star, can be enormous. So we have a computational problem. How many of these x star matrices shall we choose? Okay? So we have this difficulty. On the other hand, there is another problem here with EPPs, with expected posterior priors. Imagine a situation where P is close to n. So we have 20 observations and 15 covariates. Okay? Well, even then the idea of the minimal training sample, which is going to be, for example, 17, if you include sigma square and the beta 0, the constant term, n star then is very close to n, and therefore this prior, by definition, is going to be very informative. Okay? So this is the problem number 2. So this gives a motivation to our idea. So I'm just for 5 minutes moving to the last part of the talk, briefly tell you what we have done. So we have introduced something in order to solve these two issues that we call power expected posterior prior. And the way we thought of the problem was by combining ideas from expected posterior prior, from unit information prior, and from power prior. So what we did was the following. We started with, and I'm just telling you things very simple, but of course not so simple, but I try to make them a bit simple to your ears. So we started from the expected posterior prior, and instead of using the likelihood, that of course it's been hidden here and here, of the imaginary data, we used the power likelihood. So we took the likelihood and we raised it to a power of 1 over delta. Okay? And then we said, okay, so we're gonna set delta to be equal to n star. So immediately we made the contribution equal to 1 data point, so we made this prior unit information prior. And then, really, we can even choose n star to be equal to n, because it doesn't matter. Really, it's still going to be unit information prior. So we said, well, because it is a unit information prior, always, it doesn't matter even to take n star to be equal to n. And this, of course, it has a big advantage. Why? Because we don't have anymore the selection problem. X star, automatically, it's going to be x, since the dimensions match. Yes? Okay, so this is briefly the idea. So these are some features of this power expected posterior prior. And I'm going to show you quickly some pictures before I move quickly to a second idea, and then it's going to be the end of the talk. I like this graph. So here are, this graph shows you how sensitive our prior is to the imaginary training data sample size. Okay? So here it's n star. Here is the posterior probabilities for each covariate, explanatory variable. It's a simulated example, sorry, with 50 observations and 15 explanatory variables. And you see that really these probabilities are quite stable. Yes? So that means that no matter what n star we're using, we end up with the same results. Okay, so why not choosing n star to be equal to n and dispense with the selection of the imaginary design matrices? Okay. And this is example number 2. So this is the problem I was telling you before, when n is close to p, but still n is larger than p. So this is an example with 20 observations and 15, I think, covariates. So the minimal training sample is 17, n star is 17. So you see that n star is very close to n. And here I present you for this problem the posterior, so I just summarize the posteriors by box plots. So you see for every coefficient 2 box plots, the left one is from expected posterior prior, the right one is from the power expected posterior prior, and the solid lines are the MLEs. And you see that there are many cases where the expected posterior priors, they produce posteriors that they are not objective at all, okay? They are far away from the MLEs. Why? Because the priors are so informative in this sense. On the other hand, with the power expected posterior prior, we are always in the middle. So the median, it's always equal to the MLE, and also you can see that the variance has been reduced a lot, okay? And finally, this is idea number 2, again, very, very briefly. I'm not going to tell you details. So you remember from the middle of the talk how the power prior approach used fixed imaginary data, and how this power prior approach is strongly connected with G priors. Good. On the other hand, we have the expected posterior prior that uses random imaginary data. Yes? So the question here is, can we make a comparison, can we create a G prior that instead of using fixed imaginary data uses random imaginary data? And this is what we have done in another paper, and we call this prior PSEP. The way you can do that is to represent your prior as a mixture of G prior, but instead of placing a hyperparameter on the scale of the variance, like the people in the hyper G prior have done, we place a hyperparameter on the prior mean of the data. So we have uncertainty about the actual Y values, as a matter of fact. Okay, and we call that PSEP, and you know, I'm going to skip that. There are some calculations. This is the final prior, so you see it's a mixture. It's a G prior times predictive measure. So we do the EPP approach with G prior. We use the same ideas like PEP, so we try to diminish the effect of the training sample by using powers. Okay, so we do many calculations, we prove theorems, we have shown consistency, and we end up with, as a matter of fact, in this normal regression case, we end up with even a conjugate prior, which is good news, a normal inverse gamma prior. So inference and marginal likelihoods are readily available. And I will close with a real-life data set. So this is a famous data set among people that they do variable selection, the crime data. You can find them in R. So we have aggregate measures of the crime rate of 47 states and include 15 explanatory variables. Response variable is the rate of crimes in a particular category per head, and we have some log transform variables in order to make pictures nicer. Usually that's what people are doing. And here we have include how we have, so we have 15 explanatory variables, so we have make some comparisons. PSEP, our approach, BIC, very simple approach, G prior and hyper G prior, okay? And this is, so our approach is with circles, and this is how these probabilities for selecting each of these explanatory variables they look. So you see that for the most prominent variables, our approach does as good probably as the other approaches, but for variables that are not so good, our approach manages to give smaller weight than the other approaches. And I'm not sure how many of you are familiar with this hyper-G approach technique that many people they like to use, but one of the big drawbacks about this technique is that in general, for non-important variables, ends up to give quite high posterior inclusion probabilities. Okay, so we managed to diminish this effect. So this is a quick discussion for the last part, mostly, of the talk. So I introduce you two variants of the expected posterior priors, the PEP and the PSEP. In the PEP, we produce minimal informative priors and we sharply diminish the effect of training samples. And they have some very nice properties. With PSEPs, we explore how random imaginary data can be used to extend the G prior for normal linear models. Okay? And again, I'm telling you that there are some papers already published there is a lot of theoretical work here, but of course that would make the talk quite technical, so I try to avoid it and mostly focus on the first ideas, which I hope that there were more interest, especially the students. Thank you very much.
Thank you. We have time for a few questions, if there is any.
So I know the last part was, that's why I only spent 10 minutes, it was a bit more technical, but probably I don't know if you have any questions about, especially the first part and the whole idea, how you can do variable selection out of the Bayesian perspective. I don't know if it's clear now, at least the methodology, the idea for you, and if you have to ask me, there are probably some questions.
Thanks for the gentle introduction. I think it was very useful.
Yes, I agree.
To enter the field. I know some of you have problems with variable selections. We were discussing with
well, it's a very important area. You can find it in many different applications. And again, you know, every day, you know, there are papers that they are producing and they are on this area here. So, you know, in 45 minutes or half an hour, it's difficult to tell you everything. But at least, you know, I think from this set of slides, you have some references.
Yes.
And you can use it as the beginning of your reading.
I think it was useful to see how powerful these ideas are, especially in comparing non-nested models. And this issue arises certainly in network models.
Yes.
And this is something that you cannot do with a non-Bayesian approach.
So again, if you face a variable selection problem, please, after my talk, don't do stepwise procedures. Please, please. It's not good.
Yeah, as you said, it's suboptimal.
It's suboptimal. No, it's completely suboptimal.
And
you can do it to get a flavor, but don't trust them, really. Although, no, you know, people are still doing them.
Yeah, one
every day.
excuse is that there is software that does it automatically. But
yes.
As you've seen, there is software in
yes.
R, there are packages.
Yes, yes. And all these packages, they do different stuff, and you have a different selection also. So we can go back to this slide.
From a practical point of view.
It's good, I agree. So there are all these R packages that you can use. I think the second one, BAS, is the one that most of the people nowadays they use. It's a package that does Hyper-G, but also does G priors, BIC. So you know, you have the freedom to say which type of prior you want to use, and then you know it has some nice graphs. It gives you posterior probabilities. It can do Bayesian model average automatically for you. So you know, I think it's also quite helpful. You know, it has a nice help menu that you can read and understand exactly what it does. So I think this is a very nice package. And Bayes var selection is the last one that it's from Garcia Donato and Forte in Spain. But also they presented this in the last workshop that we were in Valencia a year ago. And also it looks very, very nice.
What if you move away from normal regression?
Well, if you move away from normal regression, there is no match. That's a problem. So Clyde, I was discussing with Clyde, and she's working on extending the bus.
Is this Merlis?
Merlis, yeah. Extending the bus for at least logistic regression. So this is something that she's doing because she just wrote a paper that I think it just was accepted in JASA about generalizing the idea of the mixtures of G priors in logistic regression setup, in GLM in general, I think. So she's going to implement the ideas behind this paper and add it to the bus, so you can do even logistic regression under this setup. Probit it's easier because it's a type of linear model, so you can always do probit, but logistic, that it's so common also, it's quite difficult. So if you want to do variable selection in logistic, there is no match, but I think soon there's going to be this bus that it's going to have logistic regression. And then, of course, you know, if there is nothing there, unfortunately, you have to put your hands and write your code, you know, and contribute to the world.
Just have a question about
Yes.
Bayesian model averaging. Bayesian model averaging, so generally you are considering all the competing models.
You don't have to consider all the computing models. So it's
you can select models.
yes. So
you
you
have a model selection problem also.
so this, if you refer to this K here, yeah, that it's up to you. So you can use a cutoff. So for example, you can calculate base factors, and you can say, well, I'm going to consider models with the base factors up to 10 or 15. So it's like a ratio that we call it. It's up to you how many models you're going to use. So it's not a very good idea, especially if your space is enormous, to include all the models, because you're going to end up with models that have tiny posterior model probabilities. So you just pick up models with some.
I mean, you can measure the select. Potentially, you can select.
Yeah. So you can do Occam's razor in a sense and use a threshold. So in their paper, Raftery and his team, they are discussing about how to select this kappa, this K. But I think this is a beautiful idea, really. And you can only do that under the Bayesian perspective, you know. And you don't ignore
model uncertainty.
Yeah, you don't ignore model uncertainty, you know. And this is an important issue here. Selecting the best model. What do you mean by best model? It's the way I started today's talk, you know. Why one model, really?
Of course, you lose in terms of interpretability.
Yes, okay.
But in terms of
But if you want to do predictions, why your predictions should be based in one only model? Especially if there is a big uncertainty about which one is this best model. If there is no uncertainty and there is a clear winner, okay, I can understand. But if there is uncertainty about which one is the best model, then why only to choose one model? Doesn't make sense. Very nice.
Okay, let's thank Dimitri.
Thank you so much. Great.
Yeah.